Okay, so in the previous slide, the text here at the bottom of the sum of forces in the y direction cut off, so I just moved it here so you can have a good view of what that is about. What I want to focus on now is to say, let's look at the fact that if you include body forces, you'll see the body forces now acting here in x and in y. What changes? Well, it's exactly the same as before the equilibrium equations. The only difference is there's a term now missing there. And the term that needs to come in essentially is the following. So that term that we need to add in is to say that the body force in the x direction multiplied now by dx, dy, and I'm going to call it the 1 for the z direction. So that's essentially now a volume gets multiplied by this Newton per meter cubed, and now it's a Newton that we get out. And now again we're back to sum of forces in the directions, in the x direction. So there will be this term that we'll add in, this term that will be carried in, that term will be carried in, and at the end then essentially what we end up with is when I pull out this dx dy, and I'm going to write it in here now. Essentially, so this term gets added here, this term gets added in here, and then what I end up with is f of x botch that one, f of x times dx dy, and the 1 is implied. Okay, so that is essentially what we have. And that is then equal to 0. And what we end up with is then plus f of x when I say this is for an operative volume and this is not 0, so this has to be 0, and then that equals to 0. So there's the body forces, and if I do the sum of forces in the y direction, I get the f of y. And if I were to do it in 3D with f of z in the z direction, I would get a sum of forces in the z direction, I would get an f of z there. And that is essentially what we end up with. So hopefully this gives you a good idea of equilibrium equations in general. Okay.